Okay, so in this chapter we've looked at how a variety of nucleophiles can add into ketones and aldehydes. We've gone over oxygen nucleophiles, nitrogen nucleophiles, sulfur nucleophiles, and hydrogen nucleophiles. The last one I wanted to look at was carbon. So how can we add carbon into a ketone or aldehyde? Well, we've seen this in a variety of ways, and we covered this a fair amount in the previous term. So let's say we've got a ketone, and I want to add in a new carbon. Specifically, I want to add in a methyl group. If we do that, what we'll be left with is a tertiary alcohol, and you can probably imagine the best reagent to use in this situation would be a Grignard reagent. So what I would use is something like methyl magnesium bromide. And if we do that, we know that this carbon right here is really nucleophilic, and all that's going to happen is it's going to attack in, kick up electrons to the oxygen, and then to quench that negative charge on the oxygen, we need to treat this with some sort of dilute acid. You can even just put water. So we've covered this a fair amount, so I'm not really going to go over the mechanism in much more detail, but I did want to show you a new one called a cyanohydrin. And we're going to cover this in more detail when we get further along through this term, but I did want to briefly show it to you. And most of it makes fairly intuitive sense. So the idea with a cyanohydrin is you react cyanide. And if we draw cyanide, cyanide is a carbon-nitrogen triple bond where the carbon has a negative charge, and then there's a countercation, often it's potassium or sodium. And in this case, the carbon is still going to act as a nucleophile. It's going to add in to the carbonyl carbon and kick electrons up to that oxygen, resulting in a tetrahedral intermediate. And I'm just going to include the carbon here so we can keep track of everything. That's step one, similar to a Grignard reaction. And then step two is to treat this with dilute acid. You have to be careful to do this in two different steps, because if you mix cyanide and acid, you could inadvertently kill yourself. So you have to be extra careful when doing this. And when you do this, you'll be left with a tetrahedral intermediate. It looks like this, and this is cyanohydrin. So it looks a lot like a Grignard reaction. We've got a carbon with a negative charge attacking a carbonyl, and then we quench it in step two with some sort of dilute aqueous acid. All right, we're going to cover some more of these reactions as we go on, specifically in the chapter about carboxylic acid derivatives, but I'll show you a sneak peek. These cyanohydrins are really versatile intermediates. If you treat it with acid and heat, what you can do is you can make a carboxylic acid. So that CN triple bond that was on there instead will be converted to a new carboxylic acid functional group. So this is a kind of clever way of making a carboxylic acid. All right, another method is to treat this with LaH, or lithium aluminum hydride, whichever you prefer, and quench it with water. If you would imagine this acting as a reducing agent, you could say, well, we've got some pi bonds in there, perhaps we would reduce those. And that's exactly what happens. In this reaction, you're going to still have this tetrahedral carbon, but this time you're going to reduce the carbon-nitrogen triple bond to a carbon-nitrogen single bond. And so you can use this to make amines. We're going to cover these reactions down below later. So I'll just write will cover later. All right. So as you can see, cyanohydrins on the face of it, they don't look that useful, but once we start using them as versatile intermediates, they become a lot more powerful. All right. The most powerful carbon nucleophile is called the Wittig reagent. So let's take a look at how this is different than a traditional carbon nucleophile. And we'll start out by looking at an overview. and then we'll dive into the mechanism. All right. So the reaction that I'm showing will work with either a ketone or an aldehyde. Doesn't really matter. Either one will work. And the reagent that we'll be using is called an Illud. And I'm just going to put one hydrogen and one R group on there. You'll often see this where the phosphorus has a positive charge and the carbon has a negative charge. Or you sometimes see it written a little bit differently, where you have a double bond and no formal charges. Either one of these work. I kind of prefer to show this method up here because the reagent on top, because it really emphasizes that the carbon is the site that has high electron density. So this is called an Illud with a Y. And when we're done, what happens is we replace the carbon-oxygen double bond with a carbon-carbon double bond. So really, this whole group right here that I'm highlighting is going to replace wherever that oxygen was on there. So it's pretty powerful. It's a good way of making new alkenes. And it tends to favor Z alkenes. All right, so let's take a look at this reaction in more detail. And I want to start off by going over preparation of Illuds. Normally, when you want to do this reaction, you have to make your Illud. So let's take a look at what's going on there. So if you recall, this pH group right here is basically just a phenyl group. So this is attached to phosphorus 3 different times. It's just a lot quicker to draw out pH than to draw all of these rings, but you get the idea. All right. So let's just stick with that shorthand version. And the phosphorus has a lone pair coming off of it. In the first reaction, what you're going to do is you're going to react it with some sort of alkyl halide, or really anything with a good leaving group. And it'll do an Sn2 reaction. So if it's doing Sn2, you can imagine that it's going to attack that carbon from the backside, and it's going to kick off this leaving group. So even though I have it shown as X, X is just code for some sort of leaving group. It could be a tosylate. If you think about what works best for Sn2 reactions, it's important to remember that methyl or primary alkyl halides work best. If we think about secondary alkyl halides, they're pretty hindered, so Sn2 is not very favorable, and tertiary alkyl halides won't do Sn2 at all. So really we need to have an unhindered alkyl halide. All right, so we'll do the Sn2 reaction. And when we do that, we're going to get a new intermediate. That looks a lot like this, and our leaving group's going to pop off, and our phosphorus will have a positive charge. We're not quite done yet, though. In the second step, what we need to do is we need to treat this with a really strong base in order to get rid of this proton. If we go back up and we look at our reagent, you can see that this carbon needs to have a negative charge on it. Right now it's neutral. We need to pluck off one of those protons to give it a negative charge. All right, that proton's fairly inert, so we have to use a strong base. So the base of choice for most chemists would be N-butyl lithium. And really all that means is you've got a butyl group coming off. And the carbon off the end of the butyl group has a negative charge. People just usually abbreviate this butyl lithium, or buly for short. And this will reach out, grab this proton, and give us the carbon with the negative charge. So let's take a look at what this intermediate looks like. Got carbon with the negative charge, got a phosphorus with the positive charge. And like I said, people will show this a few different ways. Some people will show it with a double bond between phosphorus and carbon, which looks like this. Or they'll show it in the right-hand side. People normally call this one the Illud, and they'll call this one the Phosphine. I don't really know why we have different names for two different forms of these resonance structures. It's just historically what they've been called. All right, so let's take a look at the mechanism. So now that we've got the Illud, we can really do the interesting chemistry. So I'm just going to stick with a simple ketone, acetone, and I'm going to react it with the reagent that we just created. And I'm just going to abbreviate all three of those phenyl groups as pH3. And so basically I'm just using the Illud form and I'm redrawing it down here. All right, so we've got those reagents set. As you can imagine, the carbon with the negative charge is going to want to attack the carbonyl just like the other carbon nucleophiles did, and we'll kick electrons up to the oxygen. All right, so we got the carbon that attacked in, but that carbon also has that phosphorus with 3 phenyl groups coming off of it, and that phosphorus still has a positive charge. All right, at this point, this is called a beta-ene, and the oxygen with the negative charge is going to want to dump its electron density into the positive charge on the phosphorus. So let's take a look at what happens after that step. It doesn't look very stable because we've got a phosphorus forming a 4-membered ring. Let me clean this up a little bit. I'm just going to call this PPH3. However, it's completely doable. All right, so now we've got this strained 4-membered ring. This is called an oxyphosphatane. And as you can imagine, it doesn't want to stay in that 4-membered ring. So what happens is a series of bonds will break. So this bond will break and slide over, and then that bond will break and slide over. When this happens, something unique occurs. We'll get a double bond on that lower position. So down here, we're going to form a double bond. We're going to have an R group coming off and a hydrogen group coming off. That's these positions here and here. But we also have this entire group on the top. And as you can imagine, we're going to be forming a double bond between the oxygen and phosphorus. So let's take a look at what that forms. Oops, that should just be 1 pH there. There we go. So we got 3 phenyl groups on there. And this group over here is called triphenyl phosphine oxide. This is one of the key features of this reaction. This acts as a thermodynamic trap or sink. Meaning once this is formed, this reaction will no longer be in equilibrium. It'll drive the reaction all the way to completion. And like I said, the desired product is the alkene, and the alkene that's formed is usually going to be a Z alkene. So it's a pretty useful tool for making some of these alkenes. All right, before we finish up, I wanted to show you a few examples. And I wanted to compare 2 situations. So the question is, how do we make this compound? Okay, so if we're trying to make this compound, we could propose two different routes. So let's take a look. Let's do option 1 on the top, and then we'll do option 2 underneath. All right, option 1 is making this compound where one half of it is the ketone and then the other half is the Illud. So for example, maybe this portion over here was the ketone side. Okay, so let's write that out. As you can imagine, this highlighted bond, the double bond, used to be the CO double bond. So we could say, well, maybe this is the CO double bond that was replaced and ultimately became a CC double bond. Okay, that means that this other half might have been my Illud. Okay, and if that's the case, it makes sense that we would have an Illud that looks something like this, where the carbon with the negative charge is this top carbon in the ring system. So we could imagine showing that attack. All right, so I would say this is a pretty reasonable approach. Let's do option 2, where things are kind of reversed. So just like before, we're going to break this in half. And I'll just redraw this all out. And what I mean by that is maybe this half of the molecule used to be the ketone or aldehyde. And maybe the other half was the Illud. Well, let's take a look at what that would mean. So if we had the ketone or the aldehyde, we can break this apart. And we can say, well, this used to be the CO double bond. So it must have looked something along the lines of this. So we must have had an aldehyde here and not a ketone. All right, let's take a look at what the Illud must have looked like. Okay, the Illud, if we count carbons, must have looked like this, right? So now the question is, well, both of these could, in theory, give us the product, but which one is better? So what I always like to do is I like to look at the Illuds, and I ask myself, all right, which of these is going to be the better nucleophile? And if you remember, we can look at a few different things when assessing the strength of a nucleophile. One is how stable that charge is, but I would argue it's kind of a tie here, right? Carbon with the negative versus carbon with the negative. I'd say that's a wash. The second thing we can look at is sterics. We said that things that are sterically hindered tend to be worse nucleophiles. I would say that this one is sterically hindered. Meaning the carbon with the negative charge is kind of blocked by the adjacent carbons and the triphenyl phosphine group. It's essentially a tertiary-esque carbon. So this is sterically hindered, which means that this is a bad nucleophile, which means that this is a better nucleophile on top. And I would say that this top option that we've identified here would be the best route for making our desired product. All right, so that's where we're going to stop right now. When we come back, we'll take a look at the Baeyer-Villiger oxidation and then wrap up this chapter.